Good evening, everybody. We have discussed about the star-connected source and delta-connected source and the relationship between voltage and current in balanced star connection, voltage and the relationship between sorry relationship between line voltage and phase voltage in star-connected system, relationship between line current and phase current in star-connected system in delta-connected system. Right? Okay. So here, no, right? We have yesterday we have discussed about star-connected system and delta-connected system. In star-connected system, already we have discussed about the relationship between line voltage and phase voltage, and the relationship between line current and phase current. Similarly, in case of delta connection also, we have discussed about relationship between voltage and currents. Okay, and relationship between uh, line voltage and phase voltage, and relationship between line current and phase current in delta connected form, right? Okay, so normally, right, we have two types of roads, same as we have two types of sources, as well as they have two types of loads. Okay, two types of sources. What are they? They are star connected source and delta connected source. Similarly, we have two types of loads. What are they? Star connected load and delta connected load. Okay, right. Here, this is star connected load and this is delta connected load. Already we have discussed, right? You can convert this star into delta. Okay, you can convert this star into delta. We can convert this star into delta. Okay, we have relationship between uh, impedance in star connection and impedance in delta connection. Per phase impedance or per phase impedance. So coming to star connection here, right, this is a three-phase three-wire system, whereas this is three-phase four-wire system. Here neutral wire is brought from this neutral point. So this is three-phase four-wire system, whereas this is three-phase three-wire system. Okay, all are three phases, phase one, phase R, phase Y, phase B, or phase A, phase B, phase C. Okay, all three phases will produce three voltages. Okay, so ERN, EYN, EBN are phase voltages. Okay. And right, these as physically these three windings are separated by an angle of 120 degrees from each other. Obviously, there will be 120 degrees electrical difference between all phase voltage, right? Okay, so the three phase voltage ERN, EYN, even are equal in magnitude but discuss the angle 120 degrees from each other. Okay, the same is true for line voltage. Already we have discussed, right? Right. What is line voltage and what is phase voltage? Phase voltage means the voltage between line to neutral is called phase voltage. The voltage between line to line is called line voltage. Already we have discussed, right? Okay, here the phase sequence is R by B. This is R, this is Y, this is B. Okay, line R, line Y, line B. Okay, the phase sequence is R by B. R by B, line voltage are phase voltage are ERN, EYN, EBN. Line voltage are VR by B by B, BBR, or a line voltage. Okay, already we have discussed, right? Okay, you know, this is ERN. ERN. How can I draw EYN? Okay, I can draw EYN like this. Okay, I can draw EBN like this. This is EBN. Okay, this is EYN. Okay, all are equal in magnitude but displaced by an angle 120 degrees from each other. 120 degrees from each other. Okay. This voltage lags this voltage by an angle 120 degrees. VBN lags VBN by an angle 120 degrees. Okay. 120 degrees. Again, the angle between these two would be 120 degrees. Okay. How can I draw line voltage? What is line voltage? VRY is line voltage. VRY is the phasor sum of ERN minus EYN. Okay, phasor sum of ERN and minus EYN. Okay, so ERN is there. This is ERN. Okay, I have to draw minus EYN. Okay, so this is EYN means this will be minus E by N. So phasor sum of these two voltage will be what? Phasor sum of these two voltage. Phasor sum of these two voltage will be what? VRY. Will be VRY. Okay. Anyhow, the angle between these two is 120 means the angle between these two would be 60 degrees. The angle between these two would be 30 degrees. So finally we came to know that similarly you can also draw V by B and VBR also. Already we have discussed, right? Okay, so we came to know from this phasor diagram we came to know that line voltage leads phase voltage by angle 30 degrees. Okay, so now see what is this is balanced star connected system. What is VAN? Let VAN is equal to VP RMS value at an angle 0 degrees. Means what will be VBN? VBN is equal to VP at an angle minus 120 degrees. Okay, what is VCN? VCN is equal to VP at an angle minus 240 degrees. Right? Okay, now let me write VRY. What is VRY? VRY is equal to what? Okay, you know VAN is equal to VP at an angle 0 degrees. Okay, this is phase voltage. Okay, this is phase voltage. Magnitude of phase voltage. Magnitude of phase voltage, right? Okay, so how can I write what will be magnitude of line voltage? √3 times that of phase voltage. So √3 into VP would be magnitude of line voltage. Because why? Because you know, line already we have discussed, right, the relationship between line voltage and phase voltage. Okay, see after doing this, okay, after solving this, after getting phasor sum of VRN and minus V by N, you're going to get line voltage VR by. You're going to get line voltage VR by. Okay, so that line voltage VL is equal to √3 into VP. Okay, by using parallelogram method, okay, we'll get line voltage is equal to VL is equal to √3 into VP, right? So now, if it is VP means VP is the magnitude of phase voltage means, okay, what will be the magnitude of line voltage? √3 into VP, because line voltage √3 times of phase voltage. Okay. Now coming to phase angle. Okay, √3 times of magnitude of phase voltage only, right? This is magnitude of line voltage. Okay, coming to phase angle, what will be phase angle? This is VAN is VP at an angle 0 degrees means VR by, sorry, you can write here, taken VAN, right? So you can take V AB. Otherwise, here VRN, VYN, VPN, VPN, VRN, VYN, VPN. Okay, if you take R, instead of taking ABC, if you take R by B, if you take R by B, VRN is equal to VP at an angle 0 degrees, VYN is equal to VP at an angle minus 180 degrees, VPN is equal to VP at an angle minus 240 degrees. Okay, then VRY is line voltage, right? Which is equal to root 3 times phase voltage, magnitude of phase voltage. That is okay. Coming to phase angle, in case of line voltage, you know, right? From this phasor diagram, we came to know that line voltage beats phase voltage by an angle 30 degrees. Means if it is 0 degrees, means this would be this will be ahead of 30 degrees ahead of phase voltage. Means this will be 30 degrees. The phase angle will be 30 degrees. So VRY is equal to root 3 VP at an angle 30 degrees, because this is line voltage. Line voltage leads phase voltage by an angle 30 degrees. So now coming to VRY YB. What about V by B? V by B is equal to root 3 into VP. Okay. Root 3 into VP, because line voltage is equal to root 3 times phase voltage. Okay, match the phase voltage, right? So coming to phase angle, this is VBN is corresponding phase voltage to this line voltage. VBN is corresponding phase voltage to this line voltage, right? So if this is VP at an angle minus 120 degrees, means this will be root 3 VP at an angle minus 120 plus 30 degrees, plus 30 degrees, right? Then which is equal to root 3 times VP at an angle minus 90 degrees, minus 90, right? Similarly, VRY by VR. VR is equal to root 3 times VP at an angle. This line voltage is corresponding to this phase voltage. Okay. So root 3 VP at an angle minus 240 plus 30. Then root 3 VP at an angle minus 210 degrees. Okay. Okay. VL is root 3 because you know, right? Okay. Next, coming to conclusion in star connected system, star connected source, line voltage is equal to root 3 into V phase. Okay, line voltage is equal to root 3 times of phase voltage. Yeah, root 3 times of that of phase voltage. This is only magnitude. Okay, this is magnitude of line voltage. This is magnitude of phase voltage. Okay, all line voltages are equal in magnitude. Okay, all line voltages are equal in magnitude. Okay, so after drawing all line voltage, okay, see, this is B by B, this is BBR, this is BRY. Okay, again, similar to phase voltage, all line voltage are equal in magnitude, but displaced by angle 120 degrees, similar to phase voltage. Okay. So VRY leads ERN by an angle 30 degrees. B by P leads EYN by an angle 30 degrees. Okay, means just adding 30 degrees, okay, to this phase angle of phase voltage. Okay, again adding 30 degrees. is the phase angle of phase voltage. Okay, so VAR by V by P, VBR, all are equal in magnitude and displaced by an angle 180 degrees from each other. Not only phase voltage but also line voltage are equal in magnitude but displaced by an angle 30 degrees. Sorry, displaced by an angle 120 degrees from each other. Okay, so all line voltages are equal in magnitude but displaced by an angle 120 degrees from each other. Okay, all phase voltages are equal in magnitude, displaced by an angle 120 degrees from each other. Similarly, all line voltage equal in magnitude but displaced by an angle 120 degrees from each other. And VL is equal to 3 degrees. Next one is line voltage are 30 degrees ahead of their respective phase voltage. Okay, line voltage leads phase voltage by an angle 30. Okay, coming to the relationship between line current and phase current, you know, IL is equal to IP because the current which is going to line is equal to the current going to the phase current, right? Okay, so from this, after drawing this phasor diagram, okay, see, if the load is lagging, if you connect lagging load, okay, current lags voltage. Okay, current lags voltage by an angle phi. Okay, so the angle between these two would be line voltage and phase current or line current is 30 plus phi for lagging load, 30 minus phi for leading load. Yes. Okay, power P is equal to root 3 VLIL cos phi. Okay, after including relationship between line voltage and phase voltage and line current and phase current, okay, we get total force equal to root 3 into VLIL cos phi. Okay, in case of delta connection, okay, the voltage between line to line is called line voltage. The voltage across phase is called phase voltage. As phase is connected between two lines, okay, so phase voltage is equal to line voltage. Okay, so next one, coming to the relationship between line current and phase current. Okay, so here the current which is going to the phase is phase current, the current going to this phase is phase current, the current which is going to the phase current, that is IB is the phase current going to this phase. Okay, IR, IY, IB, all are phase current, all are phase current. The current which is going through phase is called phase current. Okay, the current which is going to this line is called line current. So apply KCL at this node, you'll get IR minus IB. I1, you take I1. I1 is equal to IR minus IB. Okay, remember one thing. This is not arithmetic sum. This is phasor sum. Okay. Strictly speaking, you can write this expression like this: I1 bar is equal to IR bar minus IB bar. Okay, this is not arithmetic sum. Okay, you apply KCL at this node, then I1 is equal to IR minus IB. This is phasor sum. Okay. After drawing phasor diagram, you will come to know that IL is equal to, from this phasor diagram, IL is equal to root 3 I phase. Okay. Whereas in case of star connection, VL is equal to root 3 D phase. In case of delta connection, IL is equal to root 3 into I phase. Okay, so coming to conclusions in delta connection, all IL is equal to root 3 I phase. This is magnitude only. This is magnitude only. Okay, this is magnitude of line current. This is magnitude of phase current. IPH is magnitude of phase current. IL is magnitude of line current. I'm not including phase angle over here. Okay. So all line currents are equal in magnitude, but displays 120 degrees from each other. Okay, of course. Delta connection. Sorry. Here from this phasor diagram. Okay, this is line phase current IR, IY, IB. All phase currents are equal in magnitude but displaced by an angle 120 degrees from each other. Similarly, all line currents also displaced equal in magnitude but displaced by an angle 120 degrees from each other. Same as in case of star connection. Okay, so all line currents are displaced equal in magnitude but displaced by an angle 120 degrees from each other. Line currents are from this phasor diagram, you come to know that this is line current, this is corresponding phase current. Okay, otherwise you take this. Okay, this is what this is phase current, this is line current. Okay, the angle between these two would be 30 degrees. This is 30 degrees ahead of this. Means this is phase current. Phase current leads line current by an angle 30 degrees. Whereas in case of star connected, so star connected system, line voltage leads phase voltage by an angle 30 degrees. Whereas in case of delta connected system, phase current leads line current by an angle 30 degrees. So line current are 30 degrees behind the respective phase current. Means phase current leads line current by an angle 30 degrees. Coming to power, after using relationship between line voltage and phase voltage, and the relationship between line current and phase current in delta connected system, we'll get to know the total power P is equal to P into, after substituting all V is equal to BL and I is equal to IL by root 3, we'll get P is equal to PL for the same as in case of star connected source. The total power in both systems is same. Okay, now coming to disadvantages of the single phase system. Okay, yeah. Initial application of AC supply. See, normally for home appliances we can use single phase system. Okay, single phase system is very much enough to operate home appliances. Okay, so we have plenty of applications. That is okay. Only for domestic appliances, single phase system is required. Okay, but see, for home appliances, will run fans. Hollow home appliances, okay, can be operated with single phase supply. Single phase supply is very, it is sufficient to run all, use all domestic appliances. That's okay. Now coming to AC motor. AC motor means we have two types of AC motor: single phase motor and three phase motor. Okay. So in order to produce more amount of mechanical power, it is better to use three phase AC motors. Three phase AC motors are, in many ways, it is using three phase motors is better than single phase motors. Okay, so coming to reasons, what are the reasons for using three phase motors than single phase AC motors? Okay, single phase system was not okay. That is okay. Now, single phase induction motor is not self starting. Okay, single phase induction motor is not self starting. Okay, three phase motor is self starting. Okay, because in three phase induction motor there will be rotating magnetic field. Rotating magnetic field will be produced because of three phase supply. So it is self starting. Okay, three phase induction motor is self starting. Whereas single phase induction motor is not self starting. Okay, in order to make that self starting, we have to provide one more winding. That is, auxiliary winding is required to make that as self starting. Okay, I can make single phase induction motor as self starting motor by providing auxiliary winding. Okay. Okay, now next, coming to this efficiency and power factor. Single phase induction motor is not self starting. That is fine. That is okay. And it is having poor efficiency. It has poor efficiency and poor power factor. Okay, when compared to three phase machine, machine, okay, it is having poor power factor and poor efficiency. Okay. Yeah, coming to conclusion, single phase induction motor is not self starting, whereas three phase induction motor is self starting because of using three phase supply, rotating magnetic field is produced. Okay, coming to efficiency, it is having poor efficiency. Single phase induction motor is having poor efficiency and poor power factor. Whereas coming to this three phase induction motor, it is having better efficiency and good power factor. If it is having poor power factor, means it requires more reactive power. If it is having good power factor, means it takes less reactive power. Advantage of three phase system. Okay, you know, right? In order to produce more amount of power, we choose three phase system. So we generate three phase power. We distribute three phase power, but we utilize three phase power as well as three phase supply. Okay, some industries use three-phase supply, uh, and we use single phase supply. Okay, so for domestic appliances or home appliances, we use single phase supply. Okay, but we generate three phase supply. We generate three phase supply. We not generate single phase supply. Okay, so by generating three phase supply, we can take single phase supply from them. We already know, right? If you have star connection, neutral point is available. Okay, the voltage between line to neutral is called phase voltage. You can take that phase voltage, right? That is enough. Okay, that is one phase voltage. One phase voltage can be taken. Okay, from three phase supply. From three phase supply, you can take single phase supply. Okay, so when one phase or two phase inputs are required, they are taken from the three phase system. Okay, from three phase system, you can take single phase or two phase inputs. Next, the instantaneous power in a three phase system can be constant. Okay, whereas in case of single phase system, it is not like that, right? Okay, so in case of single phase system, this is voltage waveform. Then let me use lagging load, current lags voltage by an angle phi. Okay, so this will be current waveform. So what will be the instantaneous power? Okay, this is voltage, this is current. Okay, if you multiply both instantaneously, then from here to here you get negative like this. Okay, after this, from here to here you get. Okay, again. Here, instantaneous power is not constant. This is pulsating. Okay, in case of single phase system, instantaneous power is not constant. This is pulsating. We take average value. Average value is PA constant. Right. Average value, average power PA constant. Okay, so the instantaneous power in three phase system cannot be constant. Sorry. In case of single phase system, it cannot be constant. It is not constant. It is pulsating in case of single phase system. Whereas in case of three phase system, it is almost constant. It is almost constant, not pulsating. It is not pulsating. It is almost constant. This results in uniform power transmission and less vibration of three phase machine. So for the same amount of power, the three phase system is more economical than the single phase system. Okay. And the last one is the amount of wire required for the three phase system is less than the required for an equivalent single phase system. To transmit the same amount of power, single phase system requires more amount of power when compared to three phase system. Okay, yeah. Coming to different connections, different types of connections means here. Star connection. Okay, four possible connections. Okay, in balanced three-phase system: star star, star delta, delta delta, delta star. Star connection means star connected source, star connected load. Source is in source is star connected. Okay, whereas this is star connected load. Okay, this is having star connection, this is also having star connection. Source is having star connection, load is also having star connection. Okay. Star connected source, star connected load. Star connected source, delta connected load. Star connected, sorry, delta connected source, delta connected load. Delta connected source, star connected load. Okay, the very first one is balanced Y-Y connection. Means star connection. Okay, star connection means star connected source, star connected load. Okay, star connected source, star connected load. We join these two. Okay, join these two. Okay, we join these two. Okay. Now star connected source, we See, each phase will generate one voltage. This is VAN, VBN, okay, phase voltage, right? Okay, this source is having some source impedance. Okay, ZS is source impedance. Okay, as you are connecting these two lines, okay, this may have some impedance. Okay, this is line impedance. ZS is line impedance. So, strictly speaking, uh, ZS is source impedance, ZL is line impedance, and ZL is load. Okay, but normally, roughly speaking, will not include these two. ZS, we neglect ZS and ZL because anyhow these two are these two are very small. Okay, so we neglect ZL and ZS. Okay, strictly speaking, we have to include all impedances. Okay, ZS, ZL, Z, sorry, this is what ZI or something. Okay, line impedance Z small. This is Z capital. Okay, the total impedance would be Z by is equal to ZS plus ZL plus ZL. Okay, that is the total impedance. You can also neglect source impedance and line impedance. Okay, so ZS is equal to ZL plus ZL plus ZL. Okay, so this is balanced three phase system only. This is not unbalanced. Okay, all are equal in magnitude but displaced by an angle 180 degrees. Okay, so here, yeah, by neglecting ZS and ZL, you can take Z by is equal to ZL. Okay, you know, right? All phase voltages are equal in magnitude but displaced by an angle 180 degrees. So this is dp at an angle 0 degrees means this is dp at an angle minus 180 degrees. This is dp at an angle minus 240 degrees. This is dp at an angle minus 240 degrees. This is equal to dp at an angle plus 140 degrees. Both are same. Both are equal. Yeah, by drawing phasor diagram, you can find the relationship between line voltage and phase voltage, as well as mathematically also you can prove line voltage is equal to root 3 times phase voltage. VAB is equal to VAN plus VNB, which is equal to VAN minus VN. Already we have discussed, right? Okay, is equal to VP at an angle 0 degrees. VAN is VP at an angle 0 degrees minus VP at an angle minus 1 degree. Okay, so VP, if you make VP as common, then 1 at an angle 0 degrees minus 1 at an angle minus 1 degree, then finally you will get 2 degrees at an angle 30 degrees. Okay, here, magnitude as well as phase angle both are included here. That is the side. Okay, if AB is root 3 degree at angle, what 30 degrees means. Okay, by adding 30 degrees to this, by adding 30 degrees to this, you get an angle minus 90 degrees. At an angle minus 2 degrees already have discussed. There's no they have discussed, right? Okay, so otherwise after getting this also, after getting this anyhow, all phase voltage equal in magnitude but displaced by an angle 180. Similarly, all line voltage are equal in magnitude but displaced by an angle 180 from 0. So if you know this line voltage, then you'll get to know about other line voltage after just to add plus 120 to this. Okay, then so we get all these voltage VBC and VC. Right. You know, right? This is through the DP at an angle 30 degrees means okay, all line voltages are equal in magnitude, but it's with an angle 180 degrees. 30 degrees minus, sorry, this is not this, this is minus 150 means you will get minus 90 degrees. Again, minus 120 degrees, you will get minus 50 degrees. Already there. Okay, so finally, all equal in magnitude, all phase voltages are equal in magnitude, but difference by an angle 180. All line voltages are equal in magnitude, but difference by an angle 180.
doing star connection. By applying cable to each phase, okay, IA is equal to VAN by Z phi. Otherwise, simply you take this, you take this, you take this. This voltage is applied across this voltage, this phase voltage is applied across this. Okay, so the voltage across this is phase voltage. So simply IA is anyhow IA is phase voltage. So phase current. Okay, so simply you can write IA is equal to VAN by Z phi. You can write right. Next, all phase currents are equal in magnitude but displaced by an angle 180 degrees from each other. So if this is at an angle 0 degree, this would be VAN at an angle minus 180 by Z phi. That is IA at an angle minus 180. If it is IA at an angle 0, this is IA at an angle minus 120. This is IA at an angle minus 220. Or simply you can say this is also this is okay, VAN at an angle minus 240 degrees. You know, right? What is phase voltage? What is this is phase voltage? This is applied across this load. V what VCM. There is VCM. This is phase voltage. This is phase voltage, which is applied across this load. Okay, that the current which is going to be what IC. The current which is going to be IC. IC is equal to VCN by Z by VCN is equal to VAN at an angle minus 240 degrees. All are equal in magnitude, right? Okay, VAN is equal to VBN is equal to VCN. All are equal in magnitude at an angle minus 240 degrees. Right? Okay, so for balance system, you know, like IA plus IB plus IC equals 0 for balance system. So this is the current which is going to neutral wire is IN is equal to minus of IA plus IB plus IC, which is equal to 0. Okay, add this. Okay, you know, sum of all voltage at any instant is equal to 0. VAN at an angle minus 120 plus VAN at an angle minus 240 is equal to 0. 0 by impedance Z phi equal to 0. So it would be 0. Current will be 0. So neutral wire. Okay, this is an alternative way. Okay. Yeah,
Hello.
Yeah, hello.
Sir, sir, your voice is breaking somewhat.
Is it okay now?
Okay, sir.
I'll make my voice. Next one, here, see. Now it is okay, I think.
Okay, sir.
Thank you. Okay, so this is line impedance. Yeah, line impedance is given. Source impedance is not given. Okay, so source impedance is 0. Okay, this is line impedance. Okay, so here, this is what load impedance. Okay, so we have to add these two. Consider this as load impedance. Okay, so this is a given question. You know, right? 110 at an angle 2 degrees, 110 at an angle minus 120 degrees, 110 at an angle 2 minus 240 degrees. From this picture, we can say that all are equal in magnitude, all phase voltages are equal in magnitude, but still the angle 120 degrees from each other. Means this is balanced system. This is balanced system. Okay, balanced source. Okay, coming to this 5 minus J2 plus 10 plus J. Here also 5 minus J2 plus 10 plus J. Okay, same here also the same, right? That is the load is balanced load. Okay, source is balanced as well as load is balanced. Okay, this is balanced system. Okay, so here see after adding these two Z by is equal to 15 plus J6, that is 16.155 at an angle 21.8 degrees. Okay, so by considering this, okay, anyhow, see you connect these two points. Anyhow, the current flowing, if it is balanced system, current flowing into this would be 0. current flowing to this is zero means this potential is equal to this potential. Okay, then there is no potential. Then there is no potential between 2 points. There is no current. Means okay, this potential is equal to this potential. Okay, then voltage between these 2 points is equal to voltage at this point with respect to this point. Means voltage across this ZY is equal to applied voltage, that is equal to 1 at an angle 0 degrees. Right? Okay, so from this we can find IA is equal to 110 at an angle 0 degrees by 16.155 at an angle 21.8. 110 at an angle 0 degrees by okay, we'll get this, right? Okay, right? Okay, in star connection, in star connected load, you know, if we get IA, then we'll get IB and IC. All of this current. Okay, so all phase currents are equal in magnitude, but it's just angle 120 degrees from each other. So this is 6.81 is magnitude of IA. Okay, then we get mod IB is 6.81, mod IC is 6.81. Okay, displaced by angle 120 degrees from each other. So you add minus 120 degrees, then you get this. You add minus 120 degrees to this, then you get this. Otherwise, okay, you find this IA, right? Okay, what is IA? IA is EA10 at an angle 0 degrees by Z5, right? Okay. Similarly, you can also find IB. IB is equal to, where is IB? IB means the current which is flowing through this is IB. IB is equal to, okay, we draw these 2 points. Okay, then voltage at this point with respect to neutral is phase voltage is equal to voltage at this point with respect to this point, means voltage across ZY. Okay, so voltage across ZY is what? Voltage across ZY is Vn at an angle minus 120 degrees. VBN at an angle minus 120 degrees by ZY. Okay, so which is equal to 110 at an angle minus 120 degrees by, okay, 16.155 at an angle 21.8. Similarly, IC is equal to 110 at an angle minus 240 degrees by 16.155 at an angle 21.8 degrees. Okay, you can do like this also. You can solve like this also. Okay, coming to this star delta connection. Okay, star delta connection. Okay, star connected source, delta connected load. Okay. So now, you know, right, all our phase voltage Vn is equal to Vp at an angle 0 degrees, Vpn is equal to Vp at an angle minus 120 degrees, Vcn is equal to Vp at an angle minus 240 degrees, or Vp at an angle plus 120 degrees, both are equal. Okay. So, you know, right, in star connected system, star connected source, line voltage is equal to root 3 times that of phase voltage at an angle 30 degrees, right? Okay. Which is equal to line voltage VAB. Okay, so the voltage at this point with respect to this point is root 3 Vp at an angle 30 degrees. Right? Okay, so line voltage is line voltage VAB. This V small ab line voltage is applied across this impedance AB, applied between these two. Between A and B. Okay, so the voltage across this is line voltage. The voltage across this is line voltage. Okay, means root 3 Vp at an angle 30 degrees. If you want to find IAB is equal equal to root 3 VP at an angle 30 degrees by Z delta. Okay, so IAB is equal to DAB, or is D capital AB, that is root 3 VP at an angle 30 degrees by Z delta. You can find IAB, the current which is going to this is IAB. Okay. Similarly, you can find IBC, VBC by Z delta. Okay, what is VBC? VBC is root 3 VP, already you know, right? Is root 3 VP at an angle minus 90 degrees. Okay, you add minus 120 degrees to this, then you'll get at an angle minus 90 degrees. You know, right? In star connected system, not only phase voltage are equal in magnitude, but also not only phase voltage but also line voltage are equal in magnitude, but displayed by an angle 120 degrees from each other. So all are displayed by an angle 120 degrees from each other. Okay, this is 30 means minus 120, 90, 90 minus 90 minus 120, minus 210 degrees, minus 210 degrees, or otherwise you add 120 degrees. Okay, to this, or minus 240 degrees. So another way of solving this is by applying KVL around loop. Okay. One is also you get IAB is equal to DAB by Z. Next, star delta connection. Okay. What else? Okay, next coming to IA. Okay, we know IAB, IC. Okay, all phase current. Okay, IAB is what? IAB is line voltage by impedance. Use the current going to the impedance side. Okay, this is phase current. IAB is phase current, IC is phase current, IBC. All are phase current, Okay, the current which is going to this line is called line voltage, line current. IA is line current. Okay, now let us find IA. Okay. Here see, you know, in delta connected system, what is the relationship between line current and phase current? Okay, phase current leads line current by an angle 30 degrees. Okay, phase current, this is what is line current. I is line current. Okay, you know that line current is equal to, in terms of magnitude, line current is equal to root 3 times phase current. Root 3 times phase current, that is okay. Okay, next one is what? Line current leads phase current by an angle 30 degrees. Okay. One more thing is IL is equal to root 3 I phase, root 3 I phase. Okay, so this is what line current IL is equal to root 3 times phase current at an angle minus 30 degrees. Because here, this is what phase current, this is what line current. Okay, line current lags phase current by an angle 30 degrees. Whereas in case of star connected system, line voltage leads phase voltage by an angle 30 degrees. Whereas here, line current lags phase current by an angle 30 degrees. So IAB root 3 at an angle minus 30. Okay, minus 30 means line current lags phase current by an angle 30. All are equal in magnitude. but discussed by any 100 degrees connection. Okay, so you know the relationship between line current and phase current in case of delta connected load. Okay, instead of doing like this, you can also convert this uh, star into delta into star. You can convert this delta into star connected load. Okay, by using star to delta and delta to star connection. Either you convert delta to star load or delta load to star load. Okay, now yeah, phase sequence ABC phase sequence, star connected source, star connected source, delta connected load. A, B, we have to include voltage also. Otherwise, simply you can also draw like this. Is A, B, okay, so all voltage is neutral point. A, C, right? Okay, here you have impedance, impedance, right? Okay, so star connected source VAN is equal to what? VA is equal to 100 at an angle 110 degrees, 10 degrees. Okay, and star connected load is 8 plus J4. Okay, 8 plus J4 means we can convert this complex form into polar form. Okay, you will get this, right? Okay, VAN at an angle 10 degrees. Okay, how can I have line voltage? You know, line voltage leads phase voltage by an angle 30 degrees. Means if it is 100 at an angle, see, first of all, first one is what is the relationship between line voltage and phase voltage? Line voltage is equal to root 3 times that of phase voltage. Root 3 times that of phase voltage. Okay, this is fine. Okay, coming to phase angle. Okay, if phase voltage 100 at an angle 10 degrees means, okay, 100 at an angle 10 degrees means, what about corresponding line voltage? Line voltage leads phase voltage by an angle 30 degrees. Means if it is 10 degrees means this angle will be 40 degrees. Okay, we have that from 40 equal to 172.2 at an angle 40 degrees. You add 30 degrees to this. Okay, so what is the current which is going to is IAB. IAB is equal to the voltage between these two by impedance. Okay, the voltage between these two by impedance. The voltage between these two is line voltage, not phase voltage. This line voltage will appear across this impedance, right? So IAB is equal to PAB by Z delta. Okay, what is PAB? You know, we have okay, line voltage which is equal to VAN root 3 at an angle 40 degrees. Okay. Root 3 into 100 at an angle 40 degrees. Right. Then you get this. You can also find IBC, IJ individually or by having like this also you can find. IB is equal to IAB at an angle minus 100 degrees. So you add minus 100 degrees to this, then you will get it. You add minus 100 degrees to this, then you will get it. Okay. Coming to line current. Line currents, what is the relationship in case of what? Delta connection. In case of delta connection, line current is equal to root 3 phase current. Root 3 phase current.
line current is root 3 phase current. So root 3 into phase current. Root 3 into phase current, that is okay. That's fine. Coming to phase angle, okay. Phase current leads leads line current by an angle 30 degrees. Means if IL is I at an angle 30 degrees, I at an angle 0 degrees means I phase would be I at an angle 30 degrees. Okay, then line current lag phase current by an angle 30 degrees means IAB root 3 at an angle minus 30. Minus 30 means this lags this by an angle 30 degrees. Line current lag phase current by an angle 30 degrees. Okay, so line current lag phase current by an angle 30 degrees. Okay, it also line current lag phase current by an angle 30 degrees. Otherwise, after getting this directly minus 120. Okay, after getting this, directly you get minus 120. After adding minus 120, you get this. After adding minus 120, you get this. Or sorry, after adding plus 240, you get this. Otherwise, plus 120. One line voltage of balance star source is EAB. Means line voltage given. The source is connected to a delta connected load 28 to 90 40 degrees. Find the phase and line current. One more column. Solve this on the load. Next, delta connection. Okay, delta connection means unlike earlier case, here directly phase voltage appearing in our source. So IAB is equal to simply VAB means phase voltage only. VAB by Z delta. You get IAB. Okay, after that you find line current because as it is delta connected system, line current is equal to root 3 times that of phase current, that is IAB. Okay, IAB at an angle minus 30 minus 30. IAB is equal to what? VAB by delta. VAB by Z delta. IBC, VAB by delta. Right, so we can find out. Okay. A balanced delta connection load with impedance is given. Okay, connected to delta connected, connected to a delta connected positive sequence generator having VAB. Means delta connected load, delta connected source. Okay, so directly line voltage is equal to phase voltage. Okay, and that line voltage or phase voltage up to the across load. So simply IAB, same as previous problem, VAB by Z delta. See that at an angle 0 degrees by 25 at an angle minus 1. Okay, after getting this, you add minus 120 degrees. VAB at an angle minus 120 degrees. Okay, 36.87 minus 120 degrees. You'll get minus 83.1 degrees. Then you add plus 120 degrees. Okay, so you add plus 120 degrees to this. You add minus 120 to this. You add plus 120 or minus 240. Minus 240. That was correct. Plus 120. Then solve this. A positive sequence balanced delta connected source implies a balanced delta connected load. Delta connection. Delta connection. Okay, delta connected source, delta connected load. Okay, you can also find this. Here what line current is given. Line current is given. You have to find. All you need to find is phase current. And this is for delta connected. Delta connected source. Delta connected source. All of this is source. What's the next one? ABC. Okay. VAB is given, like I think. VAB is not given. We have to find VAB. Right? Load impedance 18 plus J12. Okay, this is also 18 plus J12, right? VAB, we have to find VAB. Oh yeah, IA is given. IA is given. Okay. You know, right? Line current. IA is equal to phase current IAB root 3 times phase current. See, line current is equal to 3 times phase current. Okay, at an angle minus 30 degrees. Minus 30 degrees. Okay, so from this IAB, you know, right? In case of delta connection, line current is equal to root 3 times phase current. Okay, let me include. Otherwise, you can also write this VAB is phase current is equal to line current IA by root 3 at an angle 30 degrees. 30 degrees. Phase current leads line current by an angle 30 degrees, and phase current is equal to line current by root 3. Okay, which is equal to 9.6 9.607. Yeah, 9.607 by root 3. You will get 5.547. You will get, sorry, 9.09, right? You are getting 5.548. 5.548. Is what? 9.609 by angle 30 degrees. Here, what is IAB? Sorry, what is IA? IA is equal to 9.609 at an angle 35 degrees. 35 degrees. Okay, if it is 0 degrees, then 30 degrees. It is 35 degrees, right? Okay, we have to this angle also. Include this angle also. After including this angle, you will get 5.548 at an angle 65 degrees. Okay. Similarly, you can find VAB
VAB means what? Voltage or this, okay. Just VAB is equal to IAB into Z. This is delta phi. Directly this phase voltage will appear across between these two points. Okay, so either you convert this into delta, otherwise you can also find this is equal to line voltage. Actually, this is phase voltage. From on source side, it is what phase voltage. Okay, phase voltage. On load side, it is line voltage. On load side, it is line voltage. Okay, so this VAB. Okay, you find phase voltage, the voltage between line to neutral. You find the voltage between line to neutral. As we have line voltage between these two points. Okay, simply VAB by root 3. Okay, you can find phase voltage. So you can also you can have the list of this. Star connected load, delta connected source. Star connected source. Star connected load. Right. Okay. So phase voltage on source side. What is phase voltage? Phase voltage is given, right? Okay. Star connected source with a line voltage. Okay. 210. 210 is line voltage as well as phase voltage on source side. Okay. So this is the voltage between two lines on load side. Okay, so you find phase voltage first. Okay, that phase voltage is equal to 210 by root 3. 210 at an angle 0 degrees by root 3. You get phase voltage. At an angle minus 30 degrees. So phase voltage lags line voltage by an angle 30 degrees. If it is 0 degrees, means add minus 30 degrees. VAN by Z by unit. Similarly, IB is equal to IA at an angle minus 100 degrees. All are displaced by an angle 100 degrees from each other. All are equal in magnitude but displaced by an angle 100 degrees from each other. Otherwise, you can also solve this IB like this. IB is equal to VBN by Z by. What is VBN? VBN is equal to VAN. What is VAN? 121.2 at an angle minus 30 minus 120 by Z by. Because VBN is equal to root 3 times VBN is equal to phase voltage VBN is equal to line voltage. Take AB BC. BC by root 3 at an angle minus 30 degrees. This is equal to VAN we get this VAN at an angle minus 30 minus 120 degrees. Coming to unbalanced three-phase system. Okay. Load impedances are unequal. Okay. Source voltages are unequal, or if load impedances are unequal. Unequal means they may have different magnitudes, they may have different phase angles. Then they are said to be unbalanced system. Unbalanced source, unbalanced load. You can say if source is having all phase voltage are unequal in magnitude, unequal in phase angle. Okay, if they are equal in magnitude, unequal in phase angle, that is also unbalanced source. Okay, coming to load, if all impedances are equal in magnitude and phase angle, then only the load is said to be balanced. Otherwise, it is unbalanced load. Okay. Unbalanced load. Okay, here VAN, VBN, VCN. Okay, so IA is equal to star connection. Star connection IA is equal to voltage for this is phase voltage by ZD. Phase voltage IA by ZD, VBN by ZD, VCN by ZD. In case of unbalanced three-phase system, IN is not equal to 0. IN is not equal to 0. In case of balanced system, IN would be 0. So this is unbalanced system. ZA is 15, ZB is this much, ZC is this much. So all are not equal in magnitude. They are different in phase angles also. So we can find IA is equal to phase voltage 100 at an angle 0 degrees by 15, 100 at an angle 120 degrees by 10 plus 15. Okay, like this 100 at an angle. Balanced, okay, balanced voltage. Balanced voltage means 100 at an angle 0 degrees. 100 at an angle 0 degrees. Next one is IP. IP is 100 at an angle minus 120 degrees. Plus 1. 100 at an angle plus 120 degrees by 6 minus J. You can find total current. IN is equal to minus of IA plus IP plus X. If you take care of minus. Yeah. This is the question. You have to find. Let me find all anyhow current in each line as well as neutral connector. Current in the neutral connector. 5 kilowatts, 8 kilowatts, 10 kilowatts. All are resistive loads. All are resistive loads. Resistive load means this is power at this load, power at this load, power at this load. Okay, what is the voltage across this load? Voltage between line to line is here line to line voltage is 100 volts. Line voltage, line voltage 400 volts. Means what is the phase voltage? 230, 231, 400 by root 3. 400 by root 3, you get 230 or 231. 231, right? Okay, so IR is what? Okay, this power. Power P is equal to VI cos phi. Anyhow, it is resistive load, so cos phi is equal to 1. Cos phi is equal to 1. So here I is equal to P by V. Okay. V is common to all. V is 230 volts. So IB is equal to 5 kilowatts by 230. IY is equal to 8 kilowatts by 230. IR is equal to 10 kilowatts by 230. IR, IY, IP. Let us find current to neutral connector. Okay, current to neutral connector means this. IN is equal to okay, fine. Do one thing. Okay. This note, this is entering all are leaving currents. Okay. All are leaving currents. So IN is equal to IR plus IY plus IB. IR plus IY plus IB. Okay, these all are magnitudes that you find. Now let us find IN. Instead of solving like this, you can solve like this by using phasor diagram. Okay. So if it is IB is equal to what? 43.5, right? 43.5 at an angle 0 degrees. At an angle 0 degrees. Okay? At an angle 0 degrees. Okay, so 43.5. Okay, right. 43.5 at an angle 0 degrees. Okay, this is 34.8 at an angle minus 120 degrees. So this is at an angle minus 240 degrees. Okay, after adding all these currents, okay, by including max as well as phase angles, okay, then we'll get IN. This is not 13, this is 15.2. This will be 18.9. 18.9. Next, delta connected load. Okay, you can find, right? Okay, you know, this is R minus JXC. This is unbalanced system. Okay, you know, line to line voltage 440 volts. Line to line voltage 440 volts. Yeah. This volts in balance start and three-phase generator. Find the phase voltage. The phase voltage you can find, right? Phase sequence is ABC. Directly VN is equal to 400 by root 3 at angle minus 30 degrees. Okay, we add minus 120, then you add plus 120. Plus 120 to this. Then you get this. Otherwise, minus 2. Because all line voltages are equal in magnitude but displayed by an angle 120 degrees from each other. Okay, so if it is minus 30 means add minus 120 to this, then you get minus 150. You add minus 120 to this. Okay, otherwise minus 140 to this. Otherwise, plus 120 to this. Then you get 231 at an angle 90 degrees. You find by taking ACB phase sequence. What is this BPM? 30 degrees minus 120 Q's BCM. The phase sequence is the next voltage. This phase attains more positive voltage. Next to this, then A, C, BN would be what? 120 at an angle minus 30 degrees plus 120. Then we get 150. Somewhere we can find this. Our homework problems. Okay, so coming to this, VA this is given. Coming to line voltage, root 3 times that of phase voltage. Coming to my code, this is root 3 times root 3 into 120. Okay, this what do we see? This is what this is line voltage, right? Okay, line voltage 30 degrees ahead of phase voltage. 30 degrees ahead of phase voltage. So you add 30 degrees to this. You add 30 degrees to this. To know corresponding line voltage. You add 30 degrees to this. Otherwise, after finding this, add minus 120, you get this. Okay, then add plus 120 to this, or minus 240 to this. Okay, you get American minus 120. You know, minus. Homework one. This was homework one. Thank you. These are all my references.